Okay, we'll get the show on the road. So this is research I did a while ago with Megan Bartlett and Nicole Thomas. And what I want to do is sort of introduce 4 points which seem a little bit unrelated, but all sort of lead to this study. So I want to talk about pseudo-neglect, near and far space and how that's processed, virtual environments, and then we'll get on to navigation asymmetries. So firstly, pseudo-neglect, I'll just go through this fairly quickly because a lot of you will be familiar with this. You'll be aware that after right parietal damage, you can get symptoms of neglect where people just ignore all things to the left side of space, and that's known as spatial neglect. But you can also get that in normal people, you and me, and that's where it happens in an intact brain. But what you've got in actual fact is a slight over-attention to the left hemispace. So instead of neglecting the left hemispace, you're actually paying a bit too much attention to the left hemispace and ignoring the right somewhat. And that happens in the majority of right-handers. So what you get, for example, with a line is if you've got the true center here, but you don't mark that, and you say, oh, where do you think the center is? People will tend to mark the line slightly to the left of true center. And what we think is happening is that they're actually paying too much attention to that left side of space. So they're over-attending to that. And what's driving that? Well, look, there's a number of different models, but just a simple way of thinking about it really is we've heard a lot about the different functions of the two sides of the brain, left hemisphere being language, but the right hemisphere seems to be more engaged with spatial processing. And look, there's actually some neuroscience research for that. So some nice research by Deschotten published in Nature Neuroscience actually found an association, a correlation between symmetry in the superior longitudinal fasciculus and pseudo-neglect. So there seems to be a neural mechanism there driving pseudo-neglect. And the idea is that activation in this side of the brain causes more attention going to the left side of space and causes an overestimation then of those features, causing that line bisection bias. That's the first thing. Whoopsie daisy. First thing I want you to know about. Second one is how the brain processes near and far space. And this has been shown in primate studies, so a study by Caggiano. And what they do is get primates to reach for different objects. And you can see them placed at different distances there, and then do single cell recordings. And what you find is that there's a group of cells which are specialized for extrapersonal space, and you can see that they're firing harder for the long distances. And then you've got another group of cells, and they're doing the exact opposite. They're firing harder for things located in near space. It seems the brain, and this is related to the things you can actually reach and things which are outside of reach. And then it makes, given that pseudo-neglect we think is an intentional mechanism, it makes sense to think that it might also be affected by near and far space, and that does seem to be the case. So what I've been talking about so far is that people are over-attending to the left side of space and over-emphasize features on the left side. But in actual fact, that seems to be only the case for things within reach. And when in actual fact, things are outside of reach, that reverses and you actually start getting an over-attention to the right side of space. I'll give you a study example of that. It's a study by Gambarini published in 2008. And what they did was to place lines either 300 millimeters or 1200 millimeters from the subject. And subjects were asked to indicate the center using either a laser pointer or a stick. And the idea there with why I use those two things is that the laser pointer, it doesn't bring anything into near space. No matter what distance it is, it's going to be out in far space. But the stick, and this is actually comes from primate studies, when you actually touch something with a stick, even though it might be a long way away, you actually bring it into your interpersonal space. The brain is coding it differently. So here are the results. So look, what we've got along the x-axis is distance from the participant going from 30 centimeters right up to 120 centimeters. And then along the y-axis, you've got the mean bisection score. And midline is 0 here. So anything above that is a right bias, and anything negative is a left bias. And that'll make Guy feel good because left is coded as negative. So, what about the results? So for the stick, let's first look at that. You can see that there's a consistent leftward bias irrespective of the viewing distance, and that's because the stick is bringing that object into near space. But the interesting thing is for the laser pointer, you can see you're not getting quite the results you'd expect here, but at the further distance, you're in actual fact getting this rightward bias. So that's the second thing I wanted you to know. The third thing is whether this occurs in virtual space. And this is the next experiment they did. So the first one was in real space, and this one is in a virtual space, and basically replicated the experiment once again using a virtual laser and a virtual stick. The graph works in the same way, and that it goes from near to far, and you've got pseudo-neglect coded along this axis. And what you can see is pretty similar sort of results. So the virtual stick, you're getting a relatively consistent leftward bias, so the normal pseudo-neglect. But for the virtual laser, you can see that it reverts to a rightward bias as the object is pointed to is further away. So this is rather neat and actually shows it's not just for physical environment, it's also occurring in a virtual environment. Fourth thing I want you to know is about navigation asymmetries. This is research we've been doing for quite a while, and sort of we had an interest in. We used to have access to a large second year class, 270 students, and we got them to stand at this point here and then walk through a doorway. The doorway was adjusted so it was just wider than them, and just to distract them a little bit, we had them firing a toy gun at a target, which they thought was terrific. They thought that was the aim of the study, whereas it was completely irrelevant. What we were interested in is whether they bumped the left or right side as they went through. And what we found, you can see over there, is they're much more likely to bump on the right-hand side than the left-hand side. And this actually comes from a study done in Bangor quite a few years ago, and we sort of managed to replicate that. They actually just asked people, which side do you tend to bump on? And people just reported anecdotally they bumped more on the right. And this was the first experimental evidence in favour of that. Since then, we've gone on done quite a bit of research, and we were using wheelchairs, both manual and electric, and got basically the same thing. We got people to remotely control the electric wheelchair, same thing. We got whether they were going in forward or reverse. We got it for that little baby there, the little scooter. And so the students just love getting around in these things, as you can imagine. We got miniature vehicles too, a toy car. And look, one thing which most probably will get brought up is we did some research with Christine Moore. She repeated one of our experiments in Switzerland because, of course, you think, is it road rules causing this? In actual fact, if anything, of course, Australia, I should say, we drive like the British on the left-hand side of the road. And the Swiss drive on the right. And she actually found a stronger bias than in the Australian population. Okay, and how do we explain this bias? We think it's to do with, you look at the door and the door is in far space and you go, right, I'm going to aim for the middle. But in actual fact, you've bisected it slightly to the right. And when you actually go for that point, you deviate towards the right-hand side. And we've got correlational evidence for that. We actually got people to first do a whole bunch of line points, and we estimated where they thought the midpoint were, and then we got them to go through the door, and we found that the people who deviated more with their line points were also the people who tended to deviate more when they actually did the task. Okay, so I've told you 4 things. That then brings us to the experiment. Does the rightward navigation bias exist in a simulated environment? It's quite possible that simulation will affect how people code near and far. Now, Gambarini did find that the results translated into a virtual environment, but we wanted to see for ourselves. And does the right bias exist for corridors as well as doorways? Now, this is Bianca opened a can of worms with a research she did, and in actual fact, she found a very, very consistent leftward bias. And we're wondering why this occurred. And one thought is that Bianca's study was conducted in corridor. And perhaps then when you're in a corridor, everything is coded as near space and you're not getting this effect. So we wanted to look at that. I think, so that's right, I've said that. So what about our study then? So this is a task we've got. We tested around, but there's a third year class we had at Flinders University. So we've got a nice sample size of 98 people. We used this really neat program that's a maze suite, which is freely available. And you just write to them and say, I'd like to use your maze task in some of my experiments. And all you have to do is acknowledge them. So it was fantastic. Here's what it looks like. You've got a sort of a plan of the room and you can draw a doorway across there. And you can see we had two conditions. One where it's just a normal doorway up the top there. And here is our corridor condition where you have to move through like that. And I'll show you a video of what it looks like in a minute. So there's three different doorway widths. We weren't particularly interested in that, but it was just to vary the task to make people think about what they're doing. But more importantly, we had two different starting positions. So sometimes people would start slightly to the left and sometimes to the right to actually make them actually move. You know, if you put them straight in front, they're just got to go dead ahead. So here's the task. So you can see there's the doorway task. And once they reach the other room, so just keep your eyes on the top one for the moment. Once they reach the other room, then it restarts and here they go through again and they're navigating it using a game controller. The other condition you can see here's the corridor and going through like that. So that's what it would look like for the subject when they're carrying out the task. And they're asked to go through the middle as closely as possible. So in terms of a task, we mark the central point as 0. If people deviated to the left, that gets a negative score. And people deviated to the right, they got a positive score. And for the doorway task, we took two measures, which is identical to the other one, but one an early point and one at the actual midpoint. And so too for the corridor task. But in this case, the early point corresponds to the entrance into that corridor. And what we predict is for the doorway, no bias when there's no doorway to go through. So the red point, you wouldn't expect them to be going left or right, but then actually as they're going through the doorway, you'd expect a right bias. For the corridor, expect a right bias as they enter that corridor, but then as they start coding it as near space, we'd actually might predict a left bias. And here are results. So what we've got along the x-axis is whether the doorway was narrow, medium, or wide. And once again, along the y-axis, we've got a measure of deviation with negative figures being leftward and positive figures being rightward. And let's first, or what we got was an effective time point, that is whether it was early or late. I should say this is just the results for the doorway. And what this indicates is that we were getting a leftward bias for the midpoint in the doorway, whereas for the early point, we were getting nothing. So let me explain that a bit more easily. So when people were going through the doorway, before they actually reached it, there was no bias either way, but when they actually went through the doorway, they were deviating towards the right. What about the corridor then? And this is a really interesting condition. We found no difference between the early and late points. So when people were going through the corridor, they deviated towards the right as they approached and entered that corridor. But even when they reached the midpoint, they were still deviating towards the right. So what we've found here, a couple of interesting things, is the right deviation was found for simulated environments. So, and what's always worried me about a lot of the setup for these experiments when they're in the real world, you've got to be really careful in the way you place things. You know, like often these deviations might be only 10, 20 millimeters or something rather. So you've got to be really careful in the way you place equipment. The beauty of this sort of thing is that we can actually be really certain about where people think they are in the environment. It can be measured more accurately. But anyway, it's nice to see in a simulated environment. The doorway, we got no bias for the early point, which is to be expected. They actually haven't entered the aperture at that stage, and a rightward bias when they did actually go through the doorway. But more interestingly, for the corridor, we got a rightward bias for the early point as people went into the corridor, but an unexpected rightward bias even when they were halfway through it. So why Bianca got the results she did, we're not quite sure, but we think it might be perhaps, and we haven't done this experiment, but where people are looking, and it might be to do with elevation. And it's known there's a link between elevation and activation of the ventral dorsal stream, which also has a connection with the left side of the brain. So it's possible as people are going through it, it's actually changing the altitude of where they're looking, and that might be affecting their behavior, but we've yet to actually test that. We do plan to do that one of these days. Okay, and just quickly, a second experiment. I'm sort of keeping on time here. So McGeorge at University of Edinburgh demonstrated a representational pseudo-neglect. And this is this classic one, the square in Milan, where people with neglect are asked to recall items, and they would recall items from the right side and not the left, even though they weren't there. So it's that classic representational neglect. But a similar sort of thing is meant to happen with pseudo-neglect. So people will recall more items from the left side compared to the right side. And we asked, does a representational form of pseudo-neglect exist in virtual maze navigation? Now, some research done by Darling demonstrated they had lines which were on the page and then disappeared, or on the screen and then disappeared. And strangely enough, they found a leftward shift in that condition. So they actually got nothing for the lines themselves, but when they disappeared, people deviated to the left, even though it was in far space, which didn't make much sense to us. There's another way of thinking about that, and it's also possible that just the fact of having to hold that item in memory and aim for it, and I'll show you the task in a minute, might increase the cognitive load, and increased cognitive load would be expected to cause a rightward shift of attention. We had doorway and line versions of the task, and I'll show them to you. This is because we're sort of interested in whether it might be a space-based or object-based attention, and whether in actual fact the sides of the door were pulling your attention one way or the other. So here's what the tasks look like. So once again, a large sample of people, 91 dextrals. We had the two versions. We've got the doorway, so you can see that in the upper pane there. And incidentally, this is what it looked like when you're approaching it. You would, your starting point was to the left, to the right. And this is what it looked like when you had your starting point to the left. So that's the doorway condition. And here's the line condition. And in both conditions, we said to people, go through as close as possible as you can to the center. And then we've got the perceptual and representational trials. So some people did it, and the doorway and the line were there throughout the whole trial. And so they could see it. And the other condition, as soon as they started moving, they would disappear. And I'll show you what that looks like. So maybe just concentrate on the top one. It'll start in a minute. There you go. So when a trial starts, look at the top one. As soon as you start moving, it disappears, and you've got to remember where you're aiming for. And so too for the doorway. And you see, as soon as you start, it disappears, and you've got to try to remember where the middle of the doorway was. Just to say that the whether people did the line or the doorway, that was a between subjects condition. And everything else is, instead of using a joystick or a gaming controller, in this case, we had a mouse and a keypad. So people were governing their speed with keys, but using a mouse to go to govern the direction. And here are results. So we've got the, along the x-axis, the perceptual and representational condition, and along the y-axis, once again, mean perception bias. And what you can see in this case is there's an effective viewing condition. So what we're finding is that, yeah, we're getting a rightward bias in the perceptual condition, which we'd expect is replicated what we found before. But when the representational condition, when actual fact those doorways or the line disappear, the bias in actual fact seems to get stronger. So in terms of discussion, rightward bias for the perceptual trials, rightward bias increased for the representational trials, and we think that load most probably provides the best explanation for that. And there seems to be a bit of a thing that when you increase the load in an attentional task, it actually seems to increase the rightward attentional bias. And there's no difference between the line and the door condition. So it doesn't seem to matter whether you've got two objects pulling your attention one way or the other, or just something on the floor. So conclusions, the rightward deviations in navigation can be observed in a simulated environment. And so this is just a really neat program. So, it's just one of those things which are made online, which make your life so good, the work that other people have done. It appears robust and found for doorways and corridors, and occurs when the aperture is even held in memory, and the task becomes quite difficult then. And somewhere we'd like to go next is virtual reality. We've now got the technology in our lab to code in virtual reality, and it'd be really interesting to see how that went. So that's it. Thanks.
Thank you very much. Any questions?
Thank you, Mike. That was interesting. Not so much a question, just a wee little comment or note that we've run an attentional elevation test of the hypothesis, and we're still finding a leftward bumping bias.
Okay.
So hopefully that will be coming out soon, and we can try and ponder more reasons why we might be finding this leftward bias. Okay.
It's
also
still in a corridor, or you move? Is it still doing it in a corridor?
It was in a corridor. Yeah.
Okay. Yeah.
In a different corridor. We're still finding a leftward bias. Mind you, that was also done in Canada. Again, I would try it in Scotland. I don't know why there would be cultural differences, because you didn't find any differences, or at least with the Sweden study, but conversations for later. Thank you.
In terms of ecological validity, you might be interested in a little anecdote from me. Many years ago, well, everything many years ago with me, isn't it? This is before I went to university. I worked in a hospital, and my job was to push patients between the ward and where they were receiving their treatment. And I had to push them down a corridor. So they were lying on a sort of motorized bed that had handlebars. And the handlebars were very odd because they had a kind of dead man's handle. But when I stopped and did something, that stopped the bed. But as soon as I let go of the handle, off it went. And without any shadow of a doubt, the chunks in the wall of the corridor showed that I deviated to the right all the time. Arguably, the bed, which was at least 2 meters long, or maybe a bit longer to take taller patients, was acting as my stick for bringing far distance into short distance, or peripersonal space.
Well, there's a whole bunch of, there's most probably, I don't know if there's a real pattern there, but with cars, you can't really look at collisions because they're so asymmetrical. But we have looked at boats, and or tried to look at boats. And so there's a famous boat crash which took out the Tasman Bridge in Tasmania, and that collided to starboard. So, but anyway, one off.
Yeah, thanks, Mike. Interesting talk. I was just wondering, what do you think about left and right lane traffic? Because I remember visiting you first time in Melbourne, and I remember being in the stairways, always bumping into people because they walked on the wrong side, which was the side I was walking on, which was the right side. So I think this left lane, right lane traffic also applies to people just walking on stairs, floors, doorways.
It does, absolutely. And I noticed when I come here from Australia, I've got to be really careful where I walk on the street. Otherwise, I'm colliding with people. So my natural tendency is to, go that way. Whereas I find here, I've got to be consciously going to the right. Otherwise, I collide. So look, and it's interesting what Bianca's got. And is it driving direction? I mean, it was probably a study worth doing again, and maybe we're in the perfect position to do it, Bianca, like if you're back in Canada and so on. But we did it once and showed that it didn't have an effect, but it would be See, and the maze task would be really easy to do it with too. Yeah, yeah. So we should talk about that. Yeah.
Okay, thank you very much.